So this is just a brief, probably 4 to 5 minute video. I'm just gonna sketch out, this framework that I call Zeta-Space. So let's write that. Zeta-Space. All right, so the way I see it is we take a cubical scaffold in just abstract space. So for example, we'll just take a point, a zero-dimensional point. Suppose as a zero cell, no embedding assumed, no embedding into Rn, etc. And then we will take, this will be hopefully become more clear as I go along, but we'll take a line segment, right, and then call this the n equals 0, n equals 0, n equals 0, n equals 1 case. So we're just building basically the poset of an n cube. As of right now, we will take the next one. Okay, n equals 2. And n equals 3. Take the poset there. All right, so what is the point? The point is we will first just zoom in on n equals 2, and we will decide to construct some filling or completion of the interior of it. So let's do that. And our requirements, we are going to have curves. So this would be, if we're measuring from n equals 2, we're going to have one-dimensional curves, and we'll say that they have to go across anti-diagonal vertices, and they have to sort of accumulate to these anti-diagonal vertices. So now we begin basically forming a CW complex within this poset. Okay, so we're going to take a sphere, right? We're going to take it with 2 cone points. It's like a twice pointed sphere. So we could go like this and create a sphere. We're going to respect the boundary. Okay, so we're going to take this. We're going to do the same over here. All right? So now these become cone points, cone point pairs across anti-diagonal vertices. Now, so this, now we're going to where they intersect here. This forms, those are the intersection points. We'll denote that to be gamma. So we'll denote that to be gamma 2 equals Let's say sigma sigma 1 intersect sigma 2, where sigma 1 and sigma 2 are just basically homeomorphic, or topologically spheres, or non-spheres, circles basically, with cone points. So have that, and sigma 2 would be also homeomorphic to S1. There you go. Now, so these are the intersection points. We want to measure that intersection locus. Okay? So now, where does it go from here is that we have, just box that. Okay. So now, we have this, we have these cone points, we have these intersections, we have these circles. Okay? So the question is, what are these, what does it look like in, say, n equals 3, n equals 1, n equals 0? Like, how does it generalize? So, well, one thing in this, and these are disjoint. So gamma, if we just measure the intersection set, so gamma is really, gamma 2 at least, is disconnected. All right, so gamma 2 is disconnected. And we'll see that this is quite different from the other dimensions here. So let's go down a dimension, dimension 1. Let's respect our constraints as per this dimension. And we'll say, so we had curves here, we'll just go down to 0 spheres, or 0 spheres. Basically get a point. Okay. And here we had intersections of 2 circles, albeit with these cone points, but now we'll do intersection of 1 0 sphere, because these are the only anti-diagonal. It's the only anti-diagonal, really. So we place one point, 0-dimensional sphere in the middle. The intersection set is the empty set. Empty set. So gamma 1 found to be the empty set. Now, let's go down another dimension. Let's go down to n equals 0. Right, so we have n equals 0, and this would be, we'd have to take All right, so a negative. So this one was a zero-dimensional sphere, so we'd have to take S negative 1 as our sort of sheets, or right, because we had curves here. We had so a pair of circles intersecting, or one single zero sphere intersecting. Now we have a negative one-dimensional zero sphere. And this case is really highly degenerate, so we're just going to define gamma 0 to be the empty set as well. So right now, and by the way, gamma, so let's write, so right here, gamma 0, gamma 1 are connected by definition. So gamma 0, gamma 1 are connected. But gamma 2 is disconnected. So gamma 2 is disconnected. What about gamma 3? What about gamma 3? Is that connected or disconnected? Let's see. So this actually explodes very, very quickly in complexity, because we're going up in codimension, or not codimension, because there's no real ambient space, but we're going up in complexity. So in n equals 3, there's a lot of complexity that explodes, whereas in n equals 2 and n equals 1 and n equals 0 have barely any complexity. And I'll try to get to what I mean by complexity. So essentially, we'll take n equals 3. We'll just do the same process. This has what, 4 pairs, 4 antipodal vertex pairs. So we'll just adjoin or attach 4 two spheres to the anti-diagonal pair set of the cube. So we'll get things like this. So if this is alpha 1, alpha 2, those are the cone points, we're going to get a sphere, two-sphere, topological two-sphere. That's really an orbifold, football orbifold. I mean, so we get that. But we get 4 copies of them. So we get this, and let's just click this like that, and we'll say, right, so these are somehow assembled into here, to this cube, where say these cone points, these alpha points are incident these antipodal vertices. So naturally we're going to get some sort of intersections in the interior, just like we got these 4 intersections. But now we're going up a dimension, so we're going to get lines as the intersections. And this is where we see that gamma sub 3 becomes connected. In fact, gamma sub 3 is an octahedral graph. So it's a bit hard to imagine first pass, but gamma sub 3 becomes an octahedral graph, at least isomorphically. It's really curved, the edges are curved. So the best way to see it is like these are just assembled, like intersecting transversely almost, if you will. They're just intersecting it all at once in the center. And then you get something like this. So if you cut via, say you have like coordinate planes, you cut via 1 coordinate plane, 2 coordinate plane, and then the third, so x, y, z. You get these 3 that you have to stitch together to form the complete K222. So they're going to be the same. So say this is the coordinate, so z equals 1/2. And we'll get something like this. So right, that's one of these guys being sliced at an angle. Traces out this, I don't want to say ellipse because that would imply an embedding into a certain space, maybe Euclidean space. But it's since I'm using the z equals 1/2, I guess we'll just go with that. So we get one elliptic section, and this follows. I mean, this just basically follows because this is like so I forgot to mention, but like we can make this to be a surface of positive constant Gaussian curvature, surface of revolution. We can put spherical metric or action angle coordinates on this. Here, this would be the action, right? Action coordinate of the metric. This would be the angular coordinate of the metric, right? So we'll just denote that. Maybe theta. And this is like, I don't know, psi. So action angle. So yeah, we get, this just is basically comes from conic section. If you have learned about that, you slice a sphere, you get a circle. But if you slice a cone, if you slice a cone at different like angles, you get like what, hyperbola, like circle, ellipse, hyperbolas, parabolas, etc. So here we're going to get a ellipse, but of course it's just to help you understand like that like truly this is not embedded in anything. It's just sitting in abstract space. So, but if we do embed it, then we'll get an ellipse. But the interesting thing is we have 4 of these. All right, 1, 2, 3, 4 intersecting all together. So gonna get another ellipse. Okay. But now we have 3 copies of this. Okay, so let's say this is z equals 1/2. This one on the right is x equals 1/2. Maybe the one in the middle is y equals 1/2. Okay, so, and obviously there are 3 copies. Okay, so we'll just take this to be the same, the y equals 1/2 slice to be the same. And what I mean by that is we take like z equals 1/2, then we're gonna take the y equals 1/2, okay? Sorry, here. Glue it along vertices or intersection points here. And then we'll take this. And now now these have to be mutually orthogonal. So imagine gluing these 3 in different orientations. Okay? Say in R3, and a cube in R3. So that basically, so these would, this outer part, it's a little bit hard to see, but like this outer part would form the intersection portion. Okay, and this outer part form the intersection part. Now this inner octahedral thing, or inner cube or square, whatever, this guy would not be an intersection. Okay. So yeah, that's about it. So basically we get that K22, K22 is connected as a graph. Thus, we get our thus we get gamma 3 is connected.